This talk is about Bayesian logic in data science, one of my favorite topics. It is one of the few areas of data science where the same concept spans statistics, data science, and artificial intelligence. Statisticians have an entire field of Bayesian statistics. Artificial intelligence has Bayesian networks and Bayesian logic. The statistical world is actually divided into two different camps. The frequenticists, sometimes they're called by other names like empiricists, and the Bayesians. And although there's a branch of statistics called empirical Bayesian statistics, for the most part, these two camps don't like each other, mostly for historical reasons, academic politics. There's no really good reason for the rift. Both camps are equally valid and can be used together. The frequenticist approach is essentially that of counting. The way you measure the probability of a coin toss is by counting a lot of coins and measuring the results. So if you toss a coin 1,000 times and it comes up head 481 times, then the odds of heads would be 48.1% based on empirical observation. It's a little bit more complicated than that, but basically their concept of probability relates to events in the real world. The Bayesian approach is a little different. Their concept of probability takes into account things like prior knowledge and your assumptions. So if you ask the Bayesian what the probability of heads on a coin toss would be, the Bayesian has a prior expectation that coin tosses are almost always completely fair based on this prior assumption. The probability would be 50%, or the probability of a coin showing heads based on prior assumptions is 0.5. Now the Bayesian will still let you do the experiment and bring in new information that will alter the probability. So if you then do the coin tosses and it's 481, then probability of head tossed based on the observations, it's now 0.481. Pretty much all probability in Bayes is based on some conditional probability you're given. This brings us to Bayes' rule. The probability of A happening given B is known or assumed is the probability of B happening given A is known or assumed times the probability of A happening divided by the probability of B happening. I'll give some examples of this in a moment. If there's one thing you get from the lecture, it's the importance of Bayes' rule, not just in data science but in the natural world. As Taleb's best-selling book, The Black Swan, argues, there's some scientific evidence that Bayes' rule is actually encoded in our brains, and that shouldn't be surprising given it's a pretty good way to construct intelligent systems. As an intelligent system is a concept of the world and a probability. So if I tell you something is a bird, you might tell me that there's a 99% or even 100% chance that it can fly, based on the fact that it's a bird and your prior knowledge and assumptions about birds. Now, if I tell you that that bird is an ostrich, well, you're going to adjust your probabilities and tell me that the new odds of this particular bird and ostrich flying are 0. Bayes' rule says that a random object can fly given that the object is a bird is the probability that a random bird can fly times the probability that a random object can fly divided by the probability that a random object is a bird. So Bayes' rule tells you exactly how to construct an intelligent system like this given a database that's already filled with objects and whether or not they're birds and whether or not they can fly. And in fact, Bayes' rule comes up over and over again in the design of artificial intelligence systems and statistics. It's just that important. There are some great free resources on Bayes' rule at Wikipedia and Khan Academy, and also all editions of the classic AI textbook, AI, A Modern Approach by Russell and Norvig, have a great section on Bayesian networks and artificial intelligence. So Bayes' rule leads naturally to artificial intelligence systems. The infamous pay-per-click man from Microsoft Word, which eventually turned into the less intrusive contextual help hints today, these are all powered by Bayesian networks. In this example, there's an initial probability that a user is a turkey. If the help system then observes that user for a while, it can determine whether or not that user can fly. And so if the user is found not to be able to fly, then using Bayes' rule and the probabilities in some database, it will update the probability that that user is a turkey. So if it observes the user flying, then the odds that the user is a turkey drop to 0. As it observes user behavior and it can make inferences about whether the user is a turkey or not, it might display different contextual helps to suspected turkeys and non-turkeys. So these AI systems that are based on Bayesian logic are called Bayesian networks, and they're a robust way to build artificial intelligence systems and an alternative to other types of expert systems like decision trees that are covered in another talk, or neural networks. And they power contextual help. There's also Bayesian statistics. In our regression modeling talk, I talk about the importance of statistical significance as well as applying business logic and business knowledge to ensure that coefficients on the regression statistic are reasonable. It's important to note that you can combine Bayesian statistics with regression modeling. For example, you can use Bayesian logic or Bayesian techniques to help better compute regression coefficients. For example, if you have an a priori business knowledge about what the inputs and outputs of a given model should be, there are advanced statistical techniques that can use Bayes' rule to compute the appropriate coefficients in the linear regression and thus help let your prior expert knowledge shape the regression model and improve its predictive power. And there are some free R packages that can implement these Bayesian techniques. Another very popular use for Bayes' rule in data science is to create classifiers. There are many ways to create a classifier. For example, various advanced regression model techniques can create classification models. Decision trees or neural networks can create a classification scheme. However, sometimes there's unique characteristics about a particular classification problem. So one example is a data set with an extremely large range, an astronomical large range of data values varying from 1 to 10 to the 10th. Even when applying standard techniques to try to reshape and better normalize this data set, it can be very difficult for traditional classification systems to handle. But a Bayesian classifier has no problem with this data set, in part because it can use some additional information, such as the overall probability of a given classification that these other schemes don't normally use as inputs. Bayesian techniques, on the whole, tend to also be very computationally efficient. Some of the examples I described might have required a large neural network to be set up, but a Bayesian statistics or Bayesian network is usually fast to compute. Unlike neural networks, they are white box, meaning that an expert can look at the setup of a Bayesian network or Bayesian statistic model and judge whether or not it seems correct and certainly figure out what seems to be going on under the hood. We've already talked about some of the great resources out there for further reading on Bayes, such as the classic AI textbook by Russell and Norwig. And in addition to the Wikipedia article on Bayes' theorem already mentioned, Bayes-related topics are such a huge area that, of course, there are many articles on Wikipedia related to topics that we just touched on in this lecture. Bayesian statistics, of course, we talked about Bayesian networks. These have their own Wikipedia articles. Bayesian inference, which is the use of Bayesian in updating decision-making probabilities in response to incoming information. We talked about this as in an AI context, but it actually has wide application in many areas outside of data science and artificial intelligence. In addition to the Wikipedia articles and the AI textbook, of course, there are the CN R modules, which include some free R modules for Bayesian inference and Bayesian shaping of regression coefficients. So if you're an R programmer, be sure to check those out. That's the end of this lecture. Thanks so much.